Hello everyone and welcome back. This is going to be hopefully the last video of this series where we are learning how to module an excavator arm in ANSA to be solved in Abaqus. And we are using only rigid bodies connected by connectors of many types. Well, there is just one rigid body for us to create in here, which is this gear. And also, we need to module these hydraulic actuators using translator connectors or axial connectors. And also, we need to create the relationship between this small gear and this larger gear. Okay, we are going to do this by using an equation, which is going to be pretty interesting as well. Okay. All right. So let's start then. If you have saved your module, which is a .ANSA file, you should open it by clicking on Open, and then search for the .ANSA file that has the setup of your module. And then here I have my own module opened, and then change the deck to Abaqus so that the database is going to show Abaqus entities. And let's deactivate the visualization of rigid body. And well, let me think here. We can create the translator connectors for the hydraulic actuators. And to do this, we need to create one point right in the middle here. Well, let's deactivate the visualization of head by clicking here. Let's go to topo module. Let me deactivate my camera. Let's create a point on COG of circle. Select these 3 points, middlemost button, and these 3 points, middlemost button, and then create point on COG of points between these and these middlemost button. Okay, so this is the first point that we need to create, and the second one is this one. Let's create a point on COG of circle. Select these 3 points, rotate and select these 3 points. Now on COG of points, select this one and this one. Okay, now the translator connector is going to be between this point and this point. For the translator connector, we need to create a local coordinate system with the x-axis along the direction of the connector. Let's open Google and search for Abaqus user's guide. And let's go to this one. For example, elements, connector elements. Let me maximize it. Connector elements. Connection type library, search for translator. Press enter until you see this part. So a translator is a type of connector that allows only displacement in the local x direction. Okay, well, this is not really the best representation of a hydraulic actuator, because a hydraulic actuator doesn't... Well, actually, let's see here the CAD. Let me think here about it. Yeah, okay. We actually need to consider something that is going to be a little more complicated than I thought. But this is going to be good because we're going to practice the usage of connectors. If I use only the hydraulic actuator, then only displacement along the direction of the connector is going to be allowed, as it's shown here in this figure. But the problem is that I need to be able to have a rotation about this bolt here. You see the axis of this bolt. I need to have rotation about the axis of this bolt. And if I simply use a translator to connect this point to this point, this type of rotation is not going to be allowed. Okay. You see here, let's scroll down. You see that the translator connector has only U1 as the available components, which means that just the displacement in the X direction, where 1 is X. And it doesn't allow rotation about any axis. So how can we solve this? To solve this, we need to create a Cartesian Cardan connector, just like we created for other regions in this module. Okay, this is going to be a little confusing at first, but you're going to understand after we finish creating it. Just follow what I'm going to do now. Let me see here. Let's create a coordinate system. Go to Abaqus deck and then coordinate rectangular. I want this coordinate system to have the x-axis along this axis here. So select these 2 points. It's just like the other Cartesian Cardans that we did. Middle mouse button. I need to rotate about y minus 90 so that the x-axis is going to be in this direction. Let me increase the size of the coordinate system by clicking here in quality criteria. Presentation parameters, scroll down, increase it to 10, apply. Okay. Now I want to create a new coordinate system. Oh, sorry, a new connector to nodes from this. Deselect from this node to let me deactivate the visualization of rigid. From this to this, middle mouse button. I'm going to put it in the connectors part. In the property, well, I'm going to create a new one. This is going to be, well, this is just going to be the Cartesian Cardan 1. I'm not going to give you special names for these. So this is going to be a Cartesian Cardan, so that we can establish a relationship between translations and rotations. Translations for Cardan, rotations for, translations for Cartesian, rotations for Cardan. The coordinate system, select question mark and select this one that we just created. And the MID could be that one that we created previously. So in this MID, in this material, or for connector, it's actually named as connector behavior. You remember that we have rotation about X allowed with no resistance. And there is a large resistance for rotation about Y and Z. And there is a considerable large resistance for translation in the X, Y, and Z directions. Press OK. Press OK. Now let's select this property that we created. Here we have the ID of it, and then press OK. Okay. Now let's activate the visualization of rigid. Now I want to do the same thing here. Zoom in this region, deactivate the visualization of rigid, coordinate system, rectangular from here to here, middle mouse button, rotation about Y minus 90, press OK. Connector to nodes from this to this, middle mouse button. Question mark here on PID. Let's copy this one, copy this one that we created just now, copy. But let's change the name to CC2 And here we should change the coordinate system also. So select these question mark, select this new coordinate system that we just created, double click, and then everything else is already configured. Press OK and select CC2, press OK. All right. Now, the next step is to, let me activate the visualization of rigid. The last step is to create the translator connector between these 2 points. Okay, just follow what I'm doing. I know that you're not understanding what is going on yet, but eventually you're going to understand. But before we create this translator connector, we should create a coordinate system where the x-axis should be from this point to this point. To do this, go to Abaqus deck, coordinate system, rectangular, select, well, you see that if I try to select this point, I'm actually going to select the coordinate system, and this is going to make that the creation of this coordinate system is not going to be correct. So deactivate the visualization of coordinate system here in the database by deactivating this. Now select this point. Now we are able to select this point. Zoom out, zoom in here, and select this point on the middle. Middle mouse button, rotation about Y minus 90. Press OK. Let's see. Now let's activate again the visualization of coordinate system. And here we have the coordinate system that we've just created. You see that the x-axis is in the direction connecting the first point that we selected and the second point that we selected. That's what I wanted. Now let's create the translator connector. So click here to nodes, select this point, and then select this point. Okay, middle mouse button, we can put it in the connectors part, and then we should create a new PID. So question mark here, right click, new, and this is going to be translator 1. Translator 1, well, here in component 1 we should select translator, and the orientation question mark should be this coordinate system that we've just created. I'm going to select here because there are 2 coordinate systems in the same position in my case. So I'm going to select the last one that we created, which is this one. The ID is 10 for me. In your case, it can be different. Now press OK. And let's double click on translator and press OK. Okay, so this is how the translator connector is represented. Another type of connector that we could use is the axial connector. Let's search for axial here in the user's guide. Press enter until we see. Let me go back to the first one. Okay, so here we have the description of the axial connector. Well, I like to use the axial connector to represent springs, for example, from suspension springs, and also to represent the shock, because we can attribute a curve of force versus velocity for axial connectors. You see that the axial connector has only displacement in the x direction available, but it doesn't block the other degrees of freedom. It allows only displacement in the x direction, but it doesn't block the other displacements and rotations. So it's a little different. You can test using the axial connector later. Okay. All right. Now the next step is to... Okay, so the next step is to include this node here that is not connected to the translator connector in a tie node set, in the tie node set of this rigid body. Let's look what is this rigid body. Double click on rigid body, and maybe this is the rotating basis. Yeah, so double click on rotating basis and copy the ID of the tie node set, which is 12. Let's go to sets, and then well, this is the set that we are interested in, this one. Right click, modify. You see that we have 2 nodes in this set. Okay, you should be very careful now, because it's very common to deselect the nodes that are in this set with no purpose. Now we should select this node, this one that is not connected to the translator connector, this one right here. Okay, this one. Now we have 3 nodes in this set, middle mouse button, and now we should do the same thing for this one. We should put this node in the tie node set of arm1 rigid body. Let's see, arm1, yeah. Double click on arm1. The ID of the tie node set is 3. Let's go to sets, search for the one with ID 3, modify content, zoom in, and select this node. We have 2 nodes. Select this one. Now we have 3 nodes. Middle mouse button, close these. Okay, so now let me explain what we did here. It's like a circuit of connectors. Let's understand what happened with this one. This node right here is connected to the rotating basis rigid body, right? And this node is also connected to this node by using the Cartesian cardon connector, in which there is resistance for translations and rotations in all directions, but rotation about X, which means that this node is going to be able to rotate with respect to this node about the X-axis. But for translations and rotations about the other axis, there is going to be some resistance. Okay? Which means that, for example, if this node here, for example, if we want to, let me isolate this connector. Select, double click on connectors, select this connector, and then right click here, show only. Let's suppose that this node tries to displace in the local one direction, local X direction to the right. So it's going to be there's going to be a larger distance between these 2 nodes. Okay. Well, to do this, it's necessary to apply a force that is going to, well, the force. Well, we have the. Let's see here. Double click on connector, select this connector, double click, and then press F2 in PID, and then press F2 in MID, and then press F2 in elasticity. You see that the stiffness in the X direction is 10,000 newtons per millimeter. So if I try to displace this node 1 millimeter to the left while keeping this one in place, then I need to apply a force of 10,000 newtons. That's the meaning of it. Okay, so there is a resistance for X, Y, Z, and for rotation about X, there is no resistance. And for rotation about Y, there is resistance. So what means rotation about Y? If it means that if this node tries to rotate with respect to this node about the local Y-axis, which is the axis numbered as 2 here, then there is going to be a resistance. Okay. All right. So, and this node right here is connected to the translator connector. And then the translator connector is connected to this node, and then this node is connected to this one by using the Cartesian card. And then this one is connected, well, this one right here is connected to the rigid body. Okay, so by doing this, we have the behavior of the translator connector that only allows displacement along the direction of the connector, in this case, because the x-axis is along this direction. And we have the Cartesian cardon here at each end that allows rotation about the local x-axis, which is this axis that we see here. Okay, this is exactly what we want. Now the last thing I want to do is to match the position of these two nodes. Let's do this. Go to Abaqus deck, match, manual, select this point, and then select this one, middle mouse button. And now we have the position of these two nodes in the same place. The position is equal for the two nodes. And let's do the same thing here. Okay. Now, file, save, just in case. All right. Now we have these two. We have these two. Well, we have these these hydraulic actuator modeled. We do this. We should do the same thing here now. Okay, I'm going to be a little faster to do this. On COG of circle, 3 points, and then 3 points here. On COG of points, and then create the coordinate system, rectangular from here to here, middle mouse button, rotation about y, minus 90. Create the Cartesian cardon connector from here to here, middle mouse button, question mark on PID. Let's copy CC2, this is CC3, and then let's just modify the coordinate system, question mark, and select this coordinate system, double click, press OK, select this PID, and press OK. Now let's do the same thing here. So let's see the CAD. Yep. Let's do the same thing here on COG of circle. The other side. On COG of points. If you select something by mistake, you can deselect it using the right mouse button. Coordinate system, two nodes, connectors part, question mark on PID, let's copy CC3, this is going to be CC4, question mark on orientation. Well, I guess I forgot to create the coordinate system. Let's create the coordinate system from here to here, middle mouse button, rotation about y, minus 90, press OK. Now let's create the connector from here to here, middle mouse button, put in the connectors part, question mark on PID. This is, well, this is CC4. Let's copy CC3, and this is going to be CC4. Question mark on the orientation, and then let's select this coordinate system that we've just created. Press OK, select CC4, press OK. Now let's create another coordinate system. And there is one thing that I forgot to mention that is very important. I'm going to mention this in the creation of this new translator connector. Firstly, let's create the coordinate system. Rectangular from deactivate the visualization of coordinate system here from this point to this point. Middle mouse button, rotation about y minus 90. Press OK. Now let's create the Cartesian cardon by 2 nodes, connector by 2 nodes. Now the important thing here is that you're going to see later that we are going to apply connector motion on this translator connector of displacement in the x direction. And there is, well, if we apply positive displacement, the nodes are going to try to get farther from each other, to separate from each other. And if we apply a negative displacement, the nodes are going to try to get together, to get near to each other. And this rule is going to only work if we select the nodes appropriately to create the translator connector. So since this local coordinate system, let me activate the visualization of coordinate system here. You see that this local coordinate system, the x-axis is going from this point to this point. And for that reason, to create the translator connector by 2 nodes, we should firstly select this point and then this point. Okay, this is very important. Because if we don't do this, if we select this point first and then this other one, if we apply a positive displacement in the boundary condition, then we are going to have the opposite effect. Well, we can do this, but we should be careful then with the sign of the displacement that we are going to apply. You're going to understand better about it when we get to apply this boundary condition. Now, middle mouse button, let's put it in the connectors part, question mark on PID. And you see that we have translator 1, let's copy it, copy. And this is going to be translator 2, but the orientation is going to be different. Question mark here. And the coordinate system in my case is the last one that I created. Double click, press OK, select translator 2, press OK. Now we should redefine the tie node set of arm1. Let's go there to set. And then here we have arm1 tie node set, modify content. We have 3 nodes. I'm going to select this node. Now we have 4 nodes in this set. Middle mouse button. Now this other node is connected to the arm2 rigid body. Let's check it. Double click on rigid body and then select arm2. Yeah. So this other one is connected to arm2. So let's go to sets. Then here we have arm2 tie nodes, modify content, and select this node. Now we have 4 nodes in this set, middle mouse button. Now the last thing is to match the position. Let's use the match function in Abaqus deck from here to here. And from here to here. Okay. Well, this is starting to looking great. We just need to do one more. Okay, let's do this. Classic topo on COG of circle. Select these 3. Select these 3. On COG of points from here to here. Abaqus deck, coordinate system, rectangular, from here to here. Rotation about y minus 90. Let's create a connector by 2 nodes from here to here. Middle mouse button, select connectors part, question mark on PID, select this one, CC4, copy. This is going to be Cartesian cardon 5, question mark on orientation. Select this coordinate system that we've just created. Click on OK. Select CC5. Click on OK. Let's do the same thing here. You see that we already have... This is going to be interesting because... Let me see here. Yeah. Okay, so this is going to be interesting because we are going to have 2 connectors and 4 nodes in the same position. Okay, we should be very careful here because you see that we have already a Cartesian cardon connecting this rigid body to this rigid body. But now we are going to have another Cartesian cardon here in the same position. But to facilitate, we are going to do one thing here. Let's go to classic topo. Just follow what I'm going to do and you're going to understand eventually. Let me deactivate my camera. And we are going to create a new point using these two, relative. Select this node, middle mouse button, and then I'm going to create a point in, well, let's see, X direction. Press 1 here to define that the direction that we are going to create a point is in the X direction with respect to this point that we created. And then the distance is going to be 5 millimeters, for example. Press OK. Now we have this point. Close this. Now you see that we have a coordinate system already here that we can use. Let's see. Double click on coordinate system. And then you see that if we position the mouse here, you see that we have this coordinate system already. Okay, you should keep the visualization of coordinate system here on. So we are going to use this coordinate system for this new Cartesian cardon. But we are going to use another point. Let's go to Abaqus deck. Let's create a new Cartesian, a new connector to nodes. From this point, you should be very careful now. From this point that we've just created, and then later we are going to match the position of this point to this position, okay? So from this point to this point. Oh, let me redo this. Connector to nodes from this to, well, why am I not, this is selecting automatically. Let me try this again. 2 nodes. Let me zoom in from this. Let me zoom in. What is going on? Let me deactivate the visualization of rigid and select this one. Well, for some reason, well, let's do one thing here. Go to classic topo, create a relative again from this point, middle mouse button, X direction, 5 millimeters. Press OK. Go to Abaqus deck. Let's create a connector to nodes from here to here. Middle mouse button. Now let's create here. Well, in this case, we can use the same PID that we used for this Cartesian cardon because it has this coordinate system defined already, which is the same coordinate system that we want, and it also has the material that we want, the connector section that we want. So in PID, question mark, and then to select the PID of this connector, you should click on it, and then you see that it's going to select in this list, and then double click on it, and then press on OK. And there we have it. We have the Cartesian cardon here. Later, I'm going to match the position of this node and this node here, so that we're going to have 4 nodes in the same position. Let's activate the visualization of rigid. Zoom out. Now I need to create the coordinate system of the translator connector. So let's create it, rectangular. Deactivate the visualization of coordinate system here. Zoom in this region, and you should select this point. Okay, this point here. You should not select this or this. You should select this one, and then the next one should be this one right here, the one in the middle. Middle mouse button, rotation about y minus 90, so that the x-axis is going to be in this direction, connecting the 2 points. Let's activate the visualization of coordinate system. Here we have the coordinate system that we created. Let's create now the connector to nodes. Now it is very important again that we first select this point. You should pay attention now. You should select this point, this node, which is one of the nodes of this coordinate of this connector that we have just created. You should select this one, okay, this one, and then you should select this one. Okay, you can't, well, if you do the inverse, then you're going to face some issues with sign convention of displacement. Okay, if you select this one first and then this one as the next. Middle mouse button, question mark on PID. Oh, let me activate my camera again. And then let's get here the PID of a translator, translator 2, copy. This is going to be translator 3. And the difference is that the coordinate system, select question mark, is going to be this last one that we created. That is here. Okay, double click, press OK, select here translator 3, and then press OK. All right, and now we have the translator connector created. Now we should just define the tie node set. Well, this node should be part of the tie node set of ARM1 rigid body. So let's go to sets. Oh, sorry, it's part of the ARM2 rigid body. Go to ARM2 tie nodes, right click, modify contents. We have 4 nodes, and then select this one. Now we have 5 nodes in this set, middle mouse button. Now, well, this is interesting because this node here can be part of the rigid body of one of these 2 rigid bodies. Connecting mechanism 1 or connecting mechanism 2. Okay, one of these 2. I guess it's better, well, I guess the most correct manner to do is to assign it to connecting mechanism 1, because the connecting mechanism 1 is connected to the connecting mechanism 2 by using the Cartesian cardinal, which means that if we connect this translator here to the connecting mechanism 1, then this translator is going to produce a force in this rigid body, connecting mechanism 1, that is going to produce a force in the connecting mechanism 2. Okay, so this is how this all is going to be connected. So let's get here set connecting mechanism 1 tie nodes, modify content, and we should include this node here, this one. Now we have 3 nodes in this set, middle mouse button. Now the last thing that we should do is to match the position of these 2 nodes to be here. Let's use the match tool manual and then select this and then this, middle mouse button, and then this and this, middle mouse button. Now we have double click on connectors and create a box selection like this. You see that we have the translator connector and then we have two Cartesian cardons in the same position. So you see that in here it shows that we have 3 connectors selected. Double click on nodes, create a box selection like this, and then you see that we have a total of 4 nodes in the same position, which is what we expected. Let's match the position now of this node from here to here, middle mouse button. Okay, now let's go to file and save. Now let me think here. I guess everything is connected. We have finally finished. Actually, there is just this gear that we should create. Let's create the rigid body of this gear now. Activate the visualization of CAD. Let's use this tool here to isolate. Select here PID. Then select this gear, middle mouse button. Go to classic mesh, length. Select everything, middle mouse button, 20. Press OK. Let's use the free algorithm. Select middle mouse button. We have the mesh. Now let's go to Abaqus deck. And then actually let's go to volume mesh deck, release. Select everything, middle mouse button. Deactivate the visualization of CAD. Let's go to Abaqus deck. Inside elements group, utilities, change type to the entities. To R3D from shell. Select everything, apply. Now double click on rigid body and select this new rigid body that was created. Double click, let's name this as gear or a small gear and press OK. Now let's click on show all. Now let's see. This gear, let me see here, connector. We have this hinge here, right? Interesting. So, let me think here what we can do. We can connect this gear to this other rigid body using a hinge connector. This is one option. Yeah, I guess this is the best option actually, but to create this hinge connector, to be sure that the x-axis is going to be aligned to this connector, we are going to use the same PID. Let's do this. Let's activate the visualization of CAD and deactivate the visualization of FE mode, of FE entities. Zoom in this region. Let's use this tool here to hide some parts. Select here PID and then hide this one and the gear. Okay. Now let's go to classic topo and let me deactivate my camera. On COG of edges, and then let's use the loop so that when I select here, I'm going to select the whole circle. Select this whole circle here, middle mouse button. Now one point was created in the COG of this circle, and I'll do the same thing here. Now we have this point created. Deactivate the visualization of CAD. We have these 2 points. Now let's create a point, on COG of points. Select these 2, middle mouse button. Now let's go to Abaqus deck, coordinate to nodes, select these 2, middle mouse button. Now the PID of this connector is going to be, well, let's click on show all here. And also let's activate the visualization of FE mode, zoom out, and then here in PID, use the question mark, and then I want to select the PID of this hinge here. Okay, so position the mouse here, select this hinge, and then the PID of this hinge is going to be selected. Double click on it. And why did I do this? Because if I select this PID and press F2 to see its properties, you see that it is a hinge and there is this coordinate system used for this connector. And I want to use the same coordinate system for this one here. And the reason for that is because I want the x-axis of these two hinges to be perfectly aligned. And so that when we have rotation with relative rotation of these two gears, then there is not going to be any forces in the other in other directions. Okay. And then we are not going to face over constraint issues, because since everything is rigid, then if there are forces in other directions and the parts are not able to deform, then we are going to face convergence issues, just like happened before. Press OK, close, and then let's deactivate the visualization of rigid. Here we have the hinge that we created. Now let's go to Sets, right click, New, select the upper node, middle mouse button. This is going to be the small gear tie node. This is a node set. Copy the ID of this tie node set, of this node set, press OK. Now double click on rigid body, double click on a small gear rigid body, and paste the ID of that node set that we created here. Press OK. Now the other node, the lower node, is going to be part of the fixed basis tie node set. Let's go to Sets. Oh, and you see that we have this new set created, which is the one that has the small gear rigid elements. Double click on this one. Let's rename it as small gear rigid elements. Press OK. Now we should get here the fixed base tie nodes. Right click, modify contents. We have only one node in this tie node set. I'm going to select this other node to be part of it. Middle mouse button. And then now that's how we connect. Let me show all. Let me activate the visualization of rigid. That's how we connect the fixed basis rigid body. And let me point out that the representation of the engine here is part of this rigid body and the small gear rigid body. That's how we connect these two. And we are using a hinge connector because we want to allow only rotation about this axis here, the x-axis, which is a vertical axis in this case. Because this gear is going to rotate about this axis for this, you see, for this shaft that we have here. This gear is going to rotate about this shaft. That's what I wanted to represent. Now, let's deactivate the visualization of rigid. And now let's use the match function manual from this one to this one, middle mouse button. Activate the visualization of rigid. And there is just one last thing that we should do. We are going to create a relationship between this gear and this gear. Let's then learn how we are going to do this relationship. Well, basically we need to create a relationship between the rotation about the axis of each gear. And let me explain how this relationship is going to be formulated. Well, we know that when we have two gears that are connected, I'm going to represent here the two gears. There is one larger gear and there is another smaller gear, right? This is what we have. If one gear rotates in the counterclockwise direction, for example, like it is shown here, we know that the other gear is going to rotate in the clockwise direction, right? We know that. Also, we know that, well, if we have the, let me represent here the diameter of the gear, So here we have the diameter of this gear. And let's say that this is the diameter of gear 1. Okay, and we are also going to have the diameter of gear 2. Diameter of gear 2. And let's say that the x-axis is the axial direction of these gears. That is, these rotations are going to be about the x-axis, okay? And I'm going to say that then, I'm going to say then that we have the gear 1 rotating about the x-axis. So we have this as the degree of freedom number 4, and this is gear 1. Okay, there is going to be a rotation like this, and gear 2 is going to rotate about its local x-axis, which is going to be a different local x-axis if compared with this one, or it could be well, yeah, it's going to be different because these ones should be passing through the center, and this one should be passing through the center. Okay. So this gear is going to have this angular velocity u42. Okay. Well, we can create a relationship between these two rotations. It's pretty easy. The relationship between these two rotations, well, we know that gear 2 is going to rotate much slower than gear 1. Okay. So we know that this is greater than this value. Sorry, this is actually the opposite. This is greater than this. Right? Let me write here an expression that correlates these two rotations. So the rotation of gear 1 is going to be equal to the diameter of gear 2 divided by the diameter of gear 1 multiplied by the rotation of gear 2. Okay, since the diameter of gear 2 is greater than the diameter of gear 1, this division is going to result in a value greater than 1. That if multiplied with the rotation of gear 2 is going to result in a rotation for gear 1 greater than the rotation of gear 2. Okay, so we can write in here that in this case, in this particular case, the rotation of gear 2 is going to be greater than the rotation of gear 1 because this gear is smaller. Okay, so how can we tell this to the software? Well, we could model these two gears as solid bodies, solid flexible bodies, create the connection, actually the contact between the teeth of the gears. We could do that, right? This would be a little more complex. This would be necessary if we wanted to actually analyze stress and strain in the gears. But in this case, the purpose of this model is different. Usually, a model like this is used to generate loads in each component of this mechanism for some specific event, such as this excavator arm grabbing something from the ground. I don't know. Okay, I'm going to talk more about how this model can be used. Okay, so how do we tell this software about this relationship? We are going to use something very interesting, that is equation constraint Abaqus. Let's click on this first link, linear constraint equations. And then here we have an explanation of how this works. So basically, this type of constraint creates a relationship between the degrees of freedom of two or more selected nodes in a way that it builds an expression that like this one shown here. A1, U1, P, where P is so U1 P is a nodal variable at node P. So P is the ID of the node, and then I is the degree of freedom. Okay, and then A2, U, J, Q, and etc. And this is all equal to 0. Well, maybe this is confusing for you, but you're going to understand how the application for our module. Well, by seeing the application for our module, you're going to understand better about this equation. Okay, so in our case, we have only 2 nodes, and we want to create a relationship between the 4th degree of freedom. Okay, so I'm going to write that expression here. Okay, so that expressions, we have that A1 multiplied by U4, or actually let me use this notation. So the superscript is the node that we are talking about. So U4 node 1. And then plus U2 degree of freedom 4 of node 2. And this is equal to 0. Okay, so that's how we are going to use this constraint, only with 2 terms, because we are going to create this relationship between 2 nodes only. So in this case, well, it's kind of confusing because here I used a different notation. So let me just to make it clear, I'm going to use the same notation here. Let me copy it to here. Yep. And also let me do this here, just to make it completely clear. Okay. Now we just need to make a correlation between this expression and this expression to find the values of A1 and A2, right? So in this expression, I could say that, well, I could pass D1 multiplying here, right? And D2 is going to simply multiply here, right? And let me think here. Oh, there is one thing that is very important that I forgot. Since the rotations are in opposite directions, one is in the counterclockwise direction and the other is in the clockwise direction, we should put a negative sign here. This is important. I forgot. Sorry. So it means that we have a negative sign here as well. Okay, now we could pass this term to the other side of the equality, but summing up. So we're going to have plus, let me copy this, and this is equal to 0. Now we can make the correlation very easily. So you see that then D1 is equal to A1 and D2 is equal to A2. Okay? All right, now let's do this in ANSA. To do this, firstly, we need to create two nodes. Okay, this is something that you're going to understand after we finish doing this. Okay, so let's just do this. We need the first node that we need is one that is going to be related to the smaller gear, and this node is going to be a tie node of the smallest gear. Okay. Let me just hide rigid, and there are 2 points here. Let me just erase these. Let's do one thing here. Let's let's show rigid. Let's search here in the database for points, and let's simply delete every point that we have created. Delete everything, because these points were created just to facilitate the creation of some entities. Now we are going to create another point. Deactivate the visualization of FE entities by clicking here, and activate the visualization of macros. Now let's go to topo module, classic topo, and then let me deactivate my camera. Okay, let's create a point on COG of edges, activate the loop tool. Now let's select this loop, this circle, select, and then meet almost button. Okay, let's do the same thing here on COG of edges. Could be this edge here, this one, select, middle mouse button. Now deactivate the visualization of macros. We have these 2 points. I know that this point is passing through the center of rotation of the greatest gear that we have in this assembly of gears, and this point is passing through the center of rotation of the smallest gear. Okay. Now what we are going to do is to create a node in these locations, because right now these are 2 points, and points are not FE entities. Points are not considered finite element entities. We should create nodes in this position. Firstly, let's activate the visualization of node here, and then to create a node entity, go to classic mesh, and then actually go to Abaqus deck, and then inside the node group, click on new, relative, and then select this point. Let's zoom in, middle mouse button, and then I want to create a point that is positioned in the same place, so I don't need to make any translation here. This function relative is to create a point relative to another point that we select, and we can apply some translation here in some direction, but in this case I want it to be in the same position, so just press OK. And well, why is it not showing there? It should show, but let me try to create a box selection. Well, for some reason it's not showing. Let me say show all. Oh yeah, let's activate the visualization of FE mode here, and deactivate the visualization of rigid. Okay, now you see that in this point we have a node, right? We have this node. I want this node to be part of the tie node set of the rotating basis. Okay, let's do this. Let's search for sets. Oh my god, sorry. Let me remove it from here. Double click on the top to remove. And then in the rotating basis tie node, right click, modify content. And then you see that we have 3 nodes, and I want to add this node that we have just created. Select, middle mouse button, and now we have 4 nodes. Okay, now let's do the same thing for the other point that we created here. Zoom in. So you see why I deleted all the other points, because now we have only 2 points and we are sure now what points we should pay attention now. Here I'm going to create a new node, new, relative, select this point, middle mouse button, and then press OK. Now we have the point created there. And I want to assign this, actually I want to add this point, this node actually, in the tie node set of the smallest gear. So let's go to sets, the small gear tie nodes, modify content. We have only 1 node, and let's include this one. Select. Now we have 2 nodes, middle mouse button. Okay. Now there is one thing here that is important. Well, I want to create an equation between these 2 nodes, but I can't create this equation directly between these 2 nodes, because these nodes are related to tie node sets, which is a type of constraint, and an equation is another type of constraint. And then if I try to create 2 constraints for these 2 nodes, then I'm going to face an over constraint issue. You can try to do this. It's a good practice to commit errors. Actually, it's a good practice to commit errors, because you're going to commit errors every day. Because in that way, you're going to learn by committing these errors. Obviously, that I committed this error and then I learned that I can't do this. Okay, so for that reason, we need to create another point, and we are going to use another type of connector, which is a good thing, because then we are going to practice another type of connector. Let's zoom in this node firstly. And now I should create here in the Abaqus tag, new relative to this node. And don't forget to let node, the visualization of node activated here, middle mouse button. And then let's create a point, for example, in the Z direction. Later we are going to match the position, so that's okay. Z direction, and by 1 millimeter. Here we have the new node. Okay. Now, let's just follow what I'm going to do here, and later you're going to understand. We're going to create a connector between these 2 nodes. A connector between these 2 nodes. And it's a new type of connector. In the Abaqus deck, go to connector 2 nodes, select this node, and then this node. Middle mouse button. We can put it in the connectors part, double click on it, and then we are going to create a new type of connector. So right click, new, and let's name this as weld, and the type of connector is going to be weld. This is a very simple type of connector because it simply tie the 2 nodes. It simply makes the 2 nodes tied together. So if one node rotates, the other node is going to rotate. See, if one node translate, the other node is going to translate. These for all degrees of freedom. Translation in all directions, rotations in all directions. Okay? It's like it's the same node, but it's, well, we have 2 nodes actually, but the 2 nodes are going to behave in the same manner. Press OK. And then double click on weld, and then click on OK. So you see that we have the weld connector created here, and we are going to do the same thing now for this node that we created previously. New, relative, select this, middle mouse button, in Z, 1 millimeter, OK. connector, 2 nodes, this one and this one, middle mouse button, connectors part, and then let's check if this is the PID of the weld, select and F2. Yes, it is in my case. If in your case it's not, press ask and then question mark, and then select here weld. Press OK and close. Okay, now the next step is to create the equation. But we are going to create the equation between this node that is not related to the tie node set. So this node is not part of any tie node set. Okay, and this node. Let's go to Abaqus deck. Inside the constraint group, we have this one, equation. Left click and hold until you see these options, and then we are going to create an equation between 2 nodes only. So zoom in here, and then it's going to be between this node that is not related to any tie node set. Zoom out and zoom in here, and then select this node. Okay, middle mouse button, and then here, in our case, it's going to be selected 1, but we want to create a relationship between the 4th degree of freedom, which is rotation about X. Press OK. And then here we are going to define this equation. So in my case, I have selected firstly this node that is going to be part of the largest gear, which means that this first line is related to the node of the largest gear, and the second line is related to the node of the smallest gear. You see that in here we have the column to define the coefficient A, and we have this column that defines the degree of freedom. You see that it's already selected rotation about X, which is the 4th degree of freedom. And in this column, we have just the ID of the node. So we saw here that A1 should be equal to the diameter of gear 1. A2 should be equal to the diameter of gear 2. We should measure these diameters. I didn't do this yet. So for now, I'm going to click on OK. And later we are going to modify this. Close, because we need to measure these diameters. Okay, but before we do this, let's zoom in here and let me think. Well, oh yeah, there is one thing that we should do here that is very important. We are creating a relationship between these 2 nodes using the 4th degree of freedom, but it turns out that for this node here, S is now the 4th degree of freedom, that is rotation about X, is this one that is shown here, the global coordinate system, which doesn't make sense for us, because if I activate the visualization of region and zoom out, rotation about the global X is not going to actually rotate this gear. Okay, so we should do here one thing. We should change the coordinate system of this node. It's possible to do this. And to do this, we are going to use a function here in Abaqus deck. That is this one. Inside the node group, in utilities, change transform. This is the function that changes the coordinate system of a node. So select this node that we want to change the coordinate system, middle mouse button, and now here we should choose the coordinate system. What is going to be the coordinate system for this one? Let's zoom out, and you see that in my case I have the coordinate system shown here. This is the one that we want, because this is the one that we used for this hinge, for this hinge, and for this hinge, for the 2 hinges of each gear. And you see that for this coordinate system, we have the x-axis in the axial direction of each gear, which is what we want. So select this coordinate system, and double click here to select. And then this is what we want. Let's do the same thing for this node. It's this node here that is connected to the equation constraint. Okay, it's not this node here. Change transform, select this node, middle mouse button, and then zoom out and select this coordinate system that is below this hinge, middle mouse button. Okay. Now, what we can do here is to match the position of these two nodes. Let's do this. Match manual from here to here, middle mouse button. And then from here to here, middle mouse button. I want it to be positioned on this point that we created previously, because I know that this point is passing through the axis of each gear, which is important. Okay, now we just need to do one thing, that is to adjust the values of A1 and A2, but for that we need to measure the diameter of each gear. To do this, deactivate the visualization of FEA entities by clicking here and activate the visualization of macros. Change here the visualization to PID so that we see this each part with a different color. And well, now we can measure the diameter of each gear. Well, we can measure this outermost diameter, we can measure the innermost diameter, but the most correct diameter is one that is in between the outermost and innermost. But in this case, I'm not going to measure the nominal diameter of the gear. I'm just going to, for example, measure the outer diameter. This relationship is going to be approximated, but it's going to be alright. You're going to see that in the animation, it's going to look pretty good. So let's do this. We're going to use this tool, measure, nodes, zoom in, select this node that is part of the outermost diameter, this node, select this one as well, for example, that is also part of the this diameter, and for example this one that is also part. And then in here select circumscribed circle, and you see that it's going to create this circle here. Okay, this looks right. And then you see that the diameter is 435. Let me write it here. So the diameter D2 is 435. Click on clear, and let's do the same thing for this gear. This node, and this node. The diameter is 65. So D1 is 65. Now, here in the database, look for constraints, maximize this group. We have the equation here, double click on it, and then you see that we have this item. We have only one equation defined, double click on it. Now, we should be very careful. Let's do one thing here. Close and right click and say show only. Now double click on node. Oh, why is it not showing the constraint anymore? Oh yeah, I should activate the visualization of FEA entities by clicking here. And we can also deactivate the visualization of CAD by clicking here. Okay, so you see that if I double click on node and select this node, the ID of this node finishes with 32. Let's memorize it. And this node is related to the largest gear. Now let's go to equation, double click on it, and then you see that this first line is related to the node that finishes with 32. Okay, so A1 should be, this is the largest gear. A1 should be D2. So it's the numbers are exchanged here compared with our model. So actually A1 here is going to be the A2 calculated here, which is 435. To change the value of A1, click once here, and then we are able to change it, 435. And the value of A2 is going to be 65. Click once here, and then 65, and that's it. Now click on OK. And well, you see that we also have the representation of the coordinate system of each node. You see that the x-axis is in the right direction. Great. Now click on Show All, deactivate the visualization of nodes, activate the visualization of rigid, zoom out, and we are almost finished. We should only adjust the boundary conditions as we want, and then we can run this model, and it's going to work perfectly. Let's do this. Well, you see that we have these 5 boundary conditions. Maximize it, and double click on boundary and select this one. So this one is to fix all degrees of freedom of the reference node of the fixed basis. And well, we yet want this to happen because this is the fixed basis and this is the one that is not going to move. This would happen even in reality when this mechanism is operating. So let me double click here, and yes, we are fixing all degrees of freedom of this node, which is the reference node of the fixed basis rigid body. So this one is not going to be modified, but the connector motions that we applied previously to rotate the hinges, well, now we are not going to do this. So right click here and then delete. Delete all connector motions and click on OK. Now, what we are going to do here is what would happen actually in reality during the operation of this mechanism, which is the hydraulic actuators would apply forces here, and then this would make the parts rotate about the Cartesian coordinates that we created. Go to Abaqus deck, and then inside the boundary group, let's create a new connector motion element. For the, let's create for this translator connector, firstly, for this one. Now let me remind you about one thing that we had done previously to create this translator connector. You see that we had created the local coordinate system for this connector going from this node to this node. We can see the coordinate system here. You see that the x-axis is upwards. It's going from this node to this node. Okay, and also when we created this connector, we first selected this node here, and then we selected this one up here. This is important because we are selecting the nodes in the direction of the local x-axis. And for that reason, now that we are going to apply this connector motion, so connector motion element, select this translator, middle mouse button. We are going to apply a displacement, a connector motion in the degree of freedom 1, which is the local x-axis of the translator. And in magnitude, we are going to define a value in millimeters. So for example, I'm going to apply here 100 millimeters of displacement. We should also define the step. I want to apply it in the first step, which is the only step that we created. And when I apply a displacement, a positive displacement, because of the way we created this translator, the way we created the coordinate system of this translator, and the way the order that we selected the nodes, this displacement is going to make the nodes separate from each other. And this is not actually what we want. We want these nodes to get nearer to each other. We want the position to be smaller from these nodes. And then we should apply a negative connector motion. Okay? Now, if we had selected these nodes in the opposite manner to create the connector, then this displacement would need to be positive. That's the only difference, actually. So you can do this, but I usually don't do this. I usually create this connector the way I just explained to you, so that I have more control over the model. Okay, press OK, and let's do the same thing for this one. Connector motion element, select the translator, middle mouse button, degree of freedom 1, which is the local x-axis, -100, step 1. Press OK. Do the same thing. Well, for this one, it's going to be different. For this translator, I actually want the nodes to separate from each other so that this arm is going to rotate in the clockwise direction here. Select this translator, middle mouse button, degree of freedom 1, and the connector motion in this case is going to be positive 100. This 100 is just an arbitrary value. I think that this is a good displacement to generate a good movement here, so we can see this moving well. Press OK. Now, how are we going to rotate the largest gear? Well, just like in what would happen in reality. In reality, this engine, this electric engine, probably an electric engine or not, I don't know. This engine here is going to rotate this shaft, that is going to rotate this small gear, that is going to rotate the largest gear, right? So we are going to then use the hinge that we created here. We are going to apply a connector motion to rotate this hinge, to cause the effect of the shaft rotating the gear. And then this gear is going to rotate the greatest gear because of the equation that we created. Okay, let's do this. Let's create a connector, let's create a connector motion element. And then let's select this connector, this hinge, middle mouse button, rotation about local x-axis, degree of freedom 4. And this rotation, well, we had seen that the smallest gear rotates much faster than the greatest gear. So this means that we should apply a great rotation, and we are going to have a small rotation in the largest gear. You're going to see this in the animation. So for example, I'm going to apply here 6 radians, which is almost 2 complete rotations, because one rotation is pi, 3.14, and 2 rotations is 2 times pi. So this is almost 2 rotations. First step, and press OK. All right, I guess that we are finished. Before we put it to run, let's go to steps, double click on step, and let me minimize this so I can see it better. In parameters of this step, remember that we define here the time period, which is like in a static analysis, it works like a percentage of load application, load or boundary condition or connector motion or anything like that. We are going to start by applying 10% of this connector motion or anything like that. And then you saw in the previous runs that if the software finds it easy to converge, then it increases the percentage of load for the next increments. But I don't want this to happen because I want to create a good animation with many points calculated. And for that, I'm going to start with 1% of load application. And you see that in this field, we can establish the maximum time increment allowed. And the maximum is going to be 1. I want this analysis to be solved 1 by 1%. If I don't define the maximum, then the software, because it's going to find it easy to convert, it's going to make the next increments larger. I don't want this to happen. Press OK. Press OK. Now let's go to compress. And then select all decks here. All decks, activate details. Roll down. Let's see if there is something that is going to be deleted. You see that we have 6 nodes that is going to be deleted. Press OK. Let's save this. Now let's go to, let's create here a working folder. Create a new folder. Let's name this as Excavator. Excavator. Mechanism. This is going to be the final module. Copy the path to this folder. Control C. And then go to File, Output, Abaqus. Paste the path to that folder here. Press Enter. Here we have it. The name of this file could be excavator.inp. Save. Let me minimize this. Version of Abaqus 2022 could be, and output all. And in comments, I'm going to deactivate the comments. Now let me minimize these, and so I can see the OK button. Click on OK. Now the output is completed, and we can run it. Well, to run it, you can open up Abaqus CAE application, just like we did before. I showed it in the first video, I guess, of this series of videos. You can import the module, create a job, and submit it. But to be more practical, we can do this by CMD command. Right-click and open in terminal. Or in your case, if you don't have this option, just search for CMD and open up the command prompt and navigate to this folder here by using the CD command. So it's going to be like copy this path and then press CD space and Control VD path to this folder. In this case, since I opened the CMD from this folder, you see that we are already in this folder here. So I don't need to navigate to this folder. Now to run this module, I should get the name of this .inp file without the extension, Ctrl C, and then type Abaqus job equals and the name of the input file without the extension. And I can also define how many threads are going to be used in this solution. I have 12 threads here in this computer, I guess. So I'm going to type CPUs equals 6, half of the number of threads, because I have OBS running here and it's pretty heavy. Press OK. Now let's go back to the working folder, and this is running. Meanwhile, I'm going to open up MetaPost, which is the post-processor software of Betakai. And then I'm going to use default layout, press OK. MetaPost is opening. If you know how to use other post-processors, you can do that. For example, if you like to use the Abaqus viewer, you can do this. I don't really like to use it. If you like to use Hyper-V, you can do this. But if you don't know how to use any post-processor software, just follow what I'm going to do here with MetaPost. Okay? Let's go back to the working folder. So the .sta file is the one that we can see the increments of the analysis. Double click on it. And then here we have what's going on. You see that it started with 1% of load application and then it's applied more 1%. So you see that it's just doing increments of 1%. Now we have 28% of the analysis. So let's wait it finish. Let me update these. We have 46% of this. Oh, and let me, meanwhile, while we wait this analysis to run, you see that we have only one step in this analysis, but this analysis is really interesting to have more than one step. Like in the first step, we are going to have some type of movement, and then on the next step, we are going to have another type of movement. Like in the first step, we are going to have this going down to grab something, and in the next step, we are going to have it going back, and then in the next step, we are going to have it rotating, and then in the next step, we are going to have it going down again to put this thing that it grabbed in another place. So this type of analysis is interesting to practice how to deal with many steps. But since this tutorial is too large, I'm not going to do this here, but if you want me to do this, if you want me to create one additional video to show how to create many steps like this, please comment in the video below. And if there are enough people asking me to do this, I'm going to create one additional video showing how to do this, okay? But right now I'm not going to do this. I'm not going to do this. Let's see here the .sta file. Yes, 90% of the analysis. Let me close this. It's almost finishing. Let's go back to this. Let's wait. Yeah, now it's finished. When it's finished, you see that just a few files are left in the folder. The other files were just temporary during the solution, okay? So what matters is the .odb file. This is the one that has the result. Let's go to MetaPost. And then in this tab, geometry, we should input the .inp file. So let's click here. And let's copy the path to this folder that we have the results and paste it here. Press enter. And then select the .inp file that has the model database. Okay, this is looking really good. Now let's go to results tab, and in my case it got the .odb file automatically in that folder. If in your case it didn't, you should just click here and then select it manually. You see that here we have the states of this analysis, which is the increments, which are the increments. We have 100 increments because we solved it 1 by 1%. Go to color tab, and here I'm going to calculate simply displacement magnitude as is selected here, and then click on read. Now we can slide this to see how this is moving. Okay, so this is working perfectly. This is really great. This is awesome. Let me deactivate the visualization of coordinate systems here. So click here in set visible entities, deactivate surface from solid, and systems. Okay. Now this is really great because you see that all the movements are occurring perfectly. This is really great. You see that, for example, for this translator connector that is represented here, since we applied a negative negative displacement, the nodes are separating from each other, which is making, oh sorry, it's not, the nodes are not separating from each other. The nodes are getting near to each other, the opposite of separating from each other. And because of that, it's pulling this up and making this rotate so that we have this movement, this rotation. Okay, the same thing is happening here for this translator connector. So you see that this green arm is rotating in the counterclockwise direction as we want it to happen. And in here we applied a positive connector motion, which is making the nodes separate from each other. And then you see this happening. This brown arm is rotating in the clockwise direction in this case. And there is this cool thing happening here between these two gears. Since we created, oh, this is really nice. It's working perfectly. Since we created that relation, well, we have intersection here, and this is not so perfect, but you see that there is a relationship between the rotation of these two gears, and it's very realistic. It's working pretty well. Okay, so the smallest gear rotates much faster than the largest gear, and this is what we wanted. And you see that, and you see why I didn't want to create good quality elements, because you see that I don't let the visualization of elements activated, so we can see that the quality is bad. We can see just the format of the element. If we zoom in and we start to notice some details, we are going to see that it's not so good. But if we look at it like this, you don't actually see that the quality of these elements is very bad. Maybe just in some regions here, you know. Anyways. Well, to finish this video, I'm going to show you how to create an animation. And also let me suggest you one thing. I know that we used so many types of connectors. We sometimes some connectors were positioned in the same place. Sometimes we used some connectors such as the weld connector because we couldn't have the equations related to the tie node set. So I would suggest you to review this whole module, to get your ANSA file and go around and just review it, and so that you're going to get used to it. And also try to get try to find in GrabCAD another excavator arm and try to model it by yourself to practice how to create these modules. Okay, it's really important to do this. Now let me show you how to create an animation of this. I actually want to create an animation looking from here, maybe. Let me see. Zoom out. Yeah, I guess this is it. Oh, zoom out. Let me see. Yeah, this is a good place. To create an animation, it's pretty simple. You should click here in record animation. And then we can create a GIF. We can create an MPGE4. I'm going to create an MPGE4. And then you see that it's going to be saved in the working folder. It's already selected here. And then in here, we can set the quality of this video. I'm going to let it as 70. I guess it goes up until 100. 100 means full quality. Here we have the output format, and here in state animation, if we let this activated, this is going to go through all these states that we have for this analysis from 0 to 100. And here we can animate only forward, backward, and forward, backward. Let's select forward, backward, because it means that it's going to go forward and then it's going to return to 0. And then in loop state, we can let it as 2. So it's going to do this whole movement. And we can activate custom duration and select it. We can define a value here for how many seconds you want this animation to last. It could be 6 seconds. And then let's give it a name such as animation, and then save. And then yes. Let's go back here to the working folder. You see that this file is being generated. It finished generating this file. Double click on it. And now we finally have our animation. Now we can post it on LinkedIn, on Facebook, on Instagram. And please mention that you learned this with me. Okay? All right. Now, let me think here. In the .inp file, double click on it. Let's open it in Notepad++. We have just the definition of this module. I'm not going to explore too much this file. You can look around. It's pretty simple. Here we have the definition of nodes, ID of the node, X coordinate, Y coordinate, and Z coordinate. If we search for asterisk element, we have the definition here of some connectors. Here we have the weld connector. We have 2 weld connectors. ID of the weld connector and ID of the nodes that this weld connector connects. And this is how the definition of the connectors are defined. You see that we have the type of element, which is this one, which means that this is a connector. Here we have the definition of the rigid elements, and then let's go to asterisk and step. And here we have the definition of the step. Okay, so it's a static, geometrical nonlinearity activated. Here we have the boundary condition fixing all degrees of freedom of the rigid body, fixed based rigid body. And here we have those connector motions that we created. Okay, so here we have the connector motions in the X direction of each translator. And here we have the connector motion of rotation about X of the smallest gear. And here we have the output request. I just requested displacement for the nodes. Okay, well, this is just a summary. I didn't go through it with many details. If you want me to explain this with more details, please let a comment below, and I can also include this in the next video if enough people asked me to do it. Okay, now I'm not going to explain in this video yet why knowing how to create a module like this is important, because I had a different idea. I'm going to actually create another video that is going to be the first video of this series, because I want to show in the first video this animation, how this works before we start creating this module. And also in this video, I'm going to explain why the creation of, well, I guess that if you are watching this video now, the end of this video, you probably have seen this first video already. Okay, so, well, that's the end of this series. I hope you liked it. I hope you learned many things by watching this series. And please subscribe to my channel, like the video, and also subscribe to my newsletter, the Learn FEA newsletter. So Learn FEA is just my blog, where I post content related to the finite element method. And that's it. I hope you liked it, and see you in the next video.